Okay, so the video froze. Question number 13. So hopefully the video will work. We'll see. So number 14 says provide the element name with ground state electron configuration 1s2 2p4. So if I look here, 2p4, what element is that? So that's period 2, block P, and the fourth element in 2p block is oxygen. So that would be your answer, oxygen. Question number 15, due to periodicity, which element would you expect to behave most like sodium? So if you look at the other answer choices, you have calcium, aluminum, and potassium. So here's calcium here, here's sodium, here's calcium, here's aluminum, and here's potassium. The potassium, you notice, is in the same column as sodium, or the same group as sodium. And so it would be the same in terms of being similar in terms of chemical reactivity in the same family. So it behaves the same or acts the same. And so potassium is the answer for that. Number 16, which of the following has the longest wavelength? And so we know X-rays are very small, and microwaves are longer than UV light waves. Number 17, elements in group 17 are considered halogens. Number 18, which of the following sets of elements are the most similar to each other? So here we have hydrogen and helium, and they're both in the same period. Carbon, nitrogen, oxygen, and fluorine all in the same period. Fluorine, chlorine, bromine, iodine, they're halogens. They're in the same group, and they're the same family. They have the family name halogens. They are most similar because elements that are in the same group have the same number of valence electrons, and they are very similar in the way they react chemically. Number 19, during a UV visible spectroscopy experiment, a student notes a wavelength peak measured at 280 nanometers. What region of the electromagnetic spectrum was this peak observed? So in general, the visible region occurs 400 to 800 nanometers, and the UV region occurs from 200 to 400 nanometers. And so 280 nanometers is within this range of UV light. Number 20, how many subshells are found in the second energy level, or shell? And so that would be S and P. So there are two subshells. If we go back to the periodic table, for the first energy level, there's one, just the S subshell. For the second energy level, there's two, the S and the P subshell. And then for the third energy level, there's three, the S, the P, and then the D. And then the fourth, there's three as well, and so on. So 2 is your answer there for that question. Alright, so here it's asking for the electron configuration of a copper atom. And so we're going to look at the periodic table here. Copper is located here, so we're going to start out with argon, and then 4s2 3d9 should be the electron configuration. However, remember, for elements that almost have a full D subshell, they're going to go ahead and pull an electron from the S subshell in order to have a completely filled D subshell. So the electron configuration is going to be AR 4s1 3d10. Okay, that also occurs for elements that have four electrons in the D subshell. Remember, they want to be halfway, so again, they'll end up taking an electron from an S subshell. These guys will, in order to halfway fill the subshell, having 5 electrons. So elements want 5 or 10 electrons in a D subshell, and so if they have 4 or 9, they're going to take one from S in order to completely fill it or to fill it up halfway. So just remember that. Those are the elements that have exceptions and that their electron configuration is a little bit different. Number 22, in what block, group, and period on the periodic table can the atom with electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5, ground state electron configuration be found? So here the last term here has P, it's in the P block, okay, and then it's in, if you look at 4p5, 4p5 is bromine, and so that's in group 7a, all right, or 17. Remember, 7a is the old notation of how to name group numbers. 17 would be the newer. So make sure you understand both the old and the new way of naming or numbering group numbers. And then the period would be 4 because there it tells you the energy value there, 4. Number 23, according to the periodic trend, which metal has the highest ionization energy? So what is ionization energy? It's the amount of energy required to remove an electron from a neutral atom. Okay, that's the first ionization energy. And so if you notice the elements here given to you, lithium, cesium, and rubidium, they're all in the group 1. Okay, so lithium's at the top here, and then you have rubidium and then cesium at the bottom. So remember your trends for ionization energy. The smaller the atom, the higher the energy. So remember we talked about it being very easy to remove an electron from a large atom because the nucleus is so far away. Okay, that electrons are easier to remove than removing an electron from a small atom where the nucleus has a greater pull on the electrons. So considering that, that would mean that lithium should have the highest ionization energy because it's the smallest atom. Number 24, a chemical reaction that absorbs energy in the form of heat is considered what? We know that chemical reactions that absorb heat are referred to as endothermic reactions. They absorb the heat of the surroundings and the surroundings get cold. Number 25, how many mole ratios can be correctly obtained from the balanced chemical equation? So here we have different coefficients. And here all I'm going to do is list the different possibilities. Okay, so 2 over 4 is a possibility. 4 over 2 is a possibility. 4 over 3 or 3 over 4 possibilities. 3 over 2 and 2 over 3 possibilities. So there's 6 different possibilities that can be utilized there. All right, for question number 26, let me zoom out here. All right, so for number 26, it says, what precipitate forms when mixing copper 2 sulfate and sodium sulfate? So here I wrote out copper 2 sulfate and sodium sulfate. And then it's two compounds here, so it's a double displacement reaction. So it's going to form copper 2 sulfate and sodium sulfate, the same products. Okay, so you have no precipitate there because they were both aqueous to begin with, and so you really don't have any reaction going on at all in that case. Number 27, here we have a volume of hydrogen gas, density of the gas, reacts with excess nitrogen gas, what mass of ammonia would be produced. So you're having to write out this chemical equation here. We have hydrogen and nitrogen, they're both diatomic molecules, and we have formation of ammonia. Okay, then I have to add these coefficients here because what happens is here I have 2 nitrogen atoms, but here I only have 1. So I have to add a 2 there to make 2 nitrogen atoms, and when I do that, that affects my hydrogen number as well. So 2 times 3 is 6 hydrogens there on the right-hand side. So I have to put a 3 here in order to balance out the hydrogens to make 6 on the left-hand side. All right, so when I take my volume and I multiply it by my density, that's going to give me the mass of hydrogen I'm starting out with. Okay, so I do that as a first step. And then I take the mass and convert that to moles using molar mass of hydrogen, which is 2 grams per mole, right? Because there's hydrogen's 1 gram per mole for each atom, and there's 2 of them. Okay. And then I use my molar ratio. So I look here, for every 3 moles of hydrogen gas, I can produce 2 moles of ammonia. And so my last step is to convert moles of ammonia now to grams of ammonia using molar mass. So I figured out my molar mass. Nitrogen's 14, hydrogen's 1 gram per atom, and there's 3 of them, so 14 plus 3 is 17. Okay, so now I do my math, 22.501 times 1 times 2 times 17, divided by 6, and I get 127.5 grams, or roughly 127 grams of ammonia produced, okay, given that scenario. Number 28 here, there are no other answer choices. I should have left, there were some answer choices there, and I think I erased them, and I should have left them. So this is the answer for this question, but it's referring to multiple equations that some of them are not balanced, or some of them are not combustion reactions. So anyways, just be expecting that possibly on the test. All right, number 29, it says how many moles of sodium hydroxide are needed to neutralize 15 milliliters of a 0.235 molar hydrochloric acid solution. So here again, I'm having to write out a chemical equation. Sodium hydroxide neutralizing hydrochloric acid, and then predicting the products. So because we have 2 compounds, again, the outsides and the insides react. So I have sodium chloride and HOH, or water. It's already balanced. Okay, I don't need to add coefficients. So I'm starting out with 0.235 moles per liter. That's the molarity of HCl. Then I multiply it by the volume in liters. Okay, so my liters cancels out, and I'm left with moles. Okay, so I'm wanting to know the moles of sodium hydroxide needed to neutralize 0.003525 moles of HCl. So all I need to do is convert moles of HCl to moles of sodium hydroxide using my molar ratio. Well, if you look, it's 1 to 1. Okay, so that means for every 1 mole of HCl, I need 1 mole of sodium hydroxide. Okay, so you see my molar ratio is 1 to 1. So that means I need 0.003525 moles of sodium hydroxide to neutralize 0.003525 moles of HCl. And that's your answer there in scientific notation, which is the same number as this. All right, so number 30 says which compound is insoluble in water. So here, calcium carbonate is insoluble. Normally these would be insoluble too, except we have group 1 metals, and so that's the exception. Group 1 metals are always soluble. And so calcium carbonate is your answer there. Number 31 is your bonus problem. It says what's the density of 0.354 molar solution of ammonium phosphate. So ammonium is NH4+, right? The +1 charge. Phosphate is PO4 -3. So you have to have 3 ammoniums to balance out the -3 charge on phosphate. So this is the information we're given. We're given molarity, so that's 0.354 moles of ammonium phosphate per liter. And then what I need to do is figure out the molar mass to figure out grams per liter, which is what density is. Density is mass per unit volume. All right, so I figure that out by ammonium has a certain mass. Okay, there's 3 of them there. There's 54, and then phosphate's 95. I add that up to get a molar mass of 149 grams per mole. Okay, so I multiply my molar mass times my molarity. Okay, and then my units are left are grams per liter. Okay, if I convert that to grams per milliliter, I get my answer, which is 0.0523 grams per milliliter. Now, I didn't specify the units, so if this were the test and you wrote this down, that would be fine too.